Shall I begin?
Yes, you can.
Okay, so thank you for this introduction. As you said, I'm Chahinaz Kandouci from University of Djillali Liabes in Algeria. I will briefly talk about my work in the performance evaluation of direct detection receivers in UWOC systems. And by UWOC systems, I mean underwater optical wireless communication systems for different water types. So we'll start by a brief introduction. A significant interest has been shown to underwater information transfer in various communication systems, not only in optical communication, but also in radio frequency and acoustic communication within the last few years. This focus is due to the fact that about 97% of the Earth is covered by oceans. This huge area had to be exploited for data transmission by the easy implementation of captors, which means avoid installing optical fibers or cables. And it has many applications in the military, the industry, the pollution and climate change monitoring, and many more. Although acoustic and radio frequency waves proved to supply a control command with this kind of applications, their data rate is still insufficient for underwater higher data rate applications, such as multimedia ones, which means that radio frequency and acoustical communication has proven to be really efficient underwater, but with small data bit rates, which is in the multimedia application is not appropriate. In this case, the substitute is to use optical waves which have the particularity to deliver higher speed rates underwater, which is what we call underwater wireless optical communication at low latency. However, this improvement engenders a limitation of the communication range. The constant increasing need for UWOC application engender many published surveys discussing physical layer aspects of the underwater optical system. So we'll briefly present the state of art of the previous work existing in this field. So firstly, Zhang et al. Focused their work on the coding technique, which means to improve the range, which is the main problem in the underwater system. They focus on the coding technique and the modulation scheme and the channel models in order to manage those systems. In Arnon and all study, the study is aimed at the performance evaluation of UWOC system links. It was evaluated for various link constraints leading to the development of a new channel characterization. In 2016, Koshal et al. Reviewed all the system modulations and scheme, and related study has been made by Johnson, which means that Koshal and Johnson studies were mostly surveyed. In most recent studies, Peng and al. Convinced multi-user diversity underwater wireless communication systems, which means that this was the first paper talking about multi-users transmission, not only one user and one transmitter and one receiver in an underwater system. It was implemented and evaluated over log normal fading channels. Lately, in 2020, Kumar and al. Introduced the use for different phase shift keying in optical wireless network with their study about a hybrid free space optical underwater wireless communication system. The main highlight of this work was the successful establishment of high data bit rates between two islands. Many other improvements in the system analyzing and channel modeling of UWOC systems has been summarized in other surveys, which means that the one I'm talking about are only the most read ones and the most famous ones, if I must say so, in the area. So the objective of our study is considering the drawbacks, which mean the range drawback and the multi-user aspects of the system, to translate the benefits of optical code division multi-access, more traditionally called OCDMA and used in optical fiber system, in the underwater wireless system, because OCDMA systems has proven to be very efficient in optical fiber system, with allowing us to have a large number of users. So we try to translate those this big cardinality or this big number of users in underwater system. So now we move to the properties of those underwater wireless channels. First of all, we have to talk about the link design. They exist under many forms. We can cite three type of configuration: the line of sight configuration, the non-line of sight configuration, and the retroreflexive links. In the presented study, we are mainly focusing on the loss link, which means the line of sight. Alors, here we can see our transmitter and our receiver separated by a distance or a range we can call D. So we have two angles that play a major part. We have, first of all, the beam divergence angle that is representing the angle of transmission of the transmitter captors, and what we call the transmitter inclination angle. So as you may guess, if this angle is too big or it's out of the beam divergence angle, the transmission will not be successful. So here, depending on those two angles, the received power will be different. Obviously, because if we receive a lot of power, we will have high performance, which means low latency, which means that the proposed system is applicable to multimedia transmissions. Here, the received power depends on the transmitted power, the range, obviously, the optical efficiency of the transmitter and the receivers, and the two angles, and obviously the attenuation coefficient. So why are we talking here about the attenuation coefficient? Because it's really important in underwater system. It will depend on the wavelength, unless if we compare it to optical fiber system, we have we generally use 1550 nanometers to maintain a low attenuation. Here we have to adapt the choice of the wavelength to our new channels, which is the water. So this is why we move now to the channel attenuation and scattering. Another important parameter to take into consideration is the attenuation coefficient C lambda. In UWOC system, it depends on the operating transmission wavelength. It's also defined as the sum of absorption and scattering coefficient, respectively, called A and B. So the absorption and scattering coefficient obviously are resulting from the particles existing in the water. They depend on the concentration of suspended and dissolved particles in the water, both of which directly affect the light beam propagation. By referring to Gerloff water classification, the typical value of absorption and scattering and extinction coefficient for different water types are listed below. We can focus on 4 different Gerloff water types: the clear water, a clear ocean, a coastal ocean, and turbid harbor. Of course, these 4 types are dependent on the chlorophyll concentration. And by then, by this table, we can have the attenuation coefficient. Obviously, it will be the smaller in clear water, where we have a minimum number of particles, and it's high in turbid harbor. So now we need to see if the implementation of the OCM-DMA system in the optical wireless channel will give good performance under those 4 constraints. So we move to the studied system. It's here represented in this figure. We will first have the spectral code. What's the spectral code? It's a combination of wavelength associated to each user. It will depend on the OCDMA codes that the family we will choose. Obviously, we can here we choose to implement code already existing in optical fiber system. The data of each user are then modulated, transmitted by the optical lens. Here we have the underwater channel, and then we will use the direct detection, followed by a demodulation and a data output. Now, what do we mean by direct detection? If each user sent a combination of wavelengths, let's take, for example, this user which sent lambda 1, lambda 4, and lambda 5. In a regular receiver, we will have to detect the 3 wavelengths using 3 different optical filters. Either they are Bessel filters or Gaussian filters, which are the most commonly used. In direct detection receivers, we can only detect 1 of the 3. There is a condition to use direct detection receiver. We need to choose code words that does not overlap, which means that no other user can use lambda 1, lambda 4, or lambda 5. using this, we will need the power of the 3 wavelengths to transmit our data, but at the receiver we can only detect one of them to have simpler receivers. It only works with 0 cross correlation codes. Which means it only works when the user has wavelengths that does not overlap. If I have here a second user that use lambda 1 and I detect it here, the performance will be bad because it will detect the data of user 1 and the data of user 2, and we will not be able to differentiate between them. So results and discussion, which means that we will implement those typical codes using simple direct detection receivers in this proposed channel. First of all, we need to talk about the parameter considered. For the most important one is the operating wavelength. Generally, in optical wireless channel, when we talk about clear water or clear oceans, we have a tendency to use blue light or green light because it gives the better effect. And when we study we make a study in coastal or turbid harbor water, we tend to use the green or the yellow one. So since the green is the common one between the two, I chose a wavelength that is close to the green color, because here we're going to make some comparison and we need to use the same wavelength in the 4 water types. We can also here see the transmission efficiency, the receiver efficiency, the bit rate, the transmitted power, and the beam divergence angle. Of course, here those parameters will be variated in order to define the system limitation. So we can first start with the range. We will consider the NRZ on-off keying modulation, which is the most commonly used in OCDMA system. Why? Because the bits 1 are considered as 1, and it have the better spectral efficiency compared to other modulation. So in order to determine the performance limitation, we need to see where the performance is limited to 10 minus 9. So here, if we make a projection, we can see that the maximum transmission distance can be a little lower than 21 meters. Which is in concordance with what we saw in the state of art, because underwater optical system only work with small ranges. Now about the cardinality or the number of users. If we variated here using a constant distance link of 10 meters, we can see that the highest number of active users that we can consider is by making a projection from 10 minus 9, the highest number can be around 10 or 11 users. As I said previously, these users have to do not overlap in their spectral signature, which means they don't have wavelength in common. If they share a wavelength, the system will not work because we are using direct detection receiver. The performance may seem a little slow, but they are in concordance with the states of art. And let's not forget that we are only detecting 1 wavelength, which means we are only detecting a third of the power we send. And we add to that the power we are losing with the attenuation coefficient. So this system is really a simple representation, a simpler system. So which means it will be less cost effective, but it gives the same results as the existing systems. So now we can compare the NRZ on-off keying modulation I was talking about with the other modulation system, the return to zero modulation and the quadratic modulation. We can see here that the other modulation allow better performance, but in optical fiber system, those modulation were never used with OCDMA. The blue one, the NRZ OOK, is the one most commonly used. So theoretically, they can give better performance, but it's an aspect that wasn't studied yet. Now, if we vary the water type, we can see here that the representation is made for clear water, clear ocean, coastal ocean, and turbid harbor, which has the higher attenuation coefficient. The necessary transmitted power to give a good an acceptable bit error rate is around 100 milliwatts for clear water. We can see 100 or 150. For clear ocean, if you want to have a good performance, we will need a little more power, obviously, because the attenuation is bigger and we are using a direct detection receiver, which means I repeat, we are only detecting a smaller part of what we send. So for clear water, for example, we will have to send the power surrounding 300 milliwatts. However, for coastal oceans or turbid harbor, even if the transmitted power is very important, we will not be able to reach a good bit error rate, bit error ratio, which means that the proposed system only works in clear water or clear oceans. We can increase the power as much as we want. It will not work with coastal or turbid harbor waters. Now let's variate the angle I was talking about. So the angle that is variated here is the one we were talking about here, which means I'm variated phi, the transmission inclination angle. We already said that looking at this picture, that if it's out of the beam divergence, obviously we will not have good results. But what's the limit of this transmitter inclination angle? So yes, we were here. For clear water, obviously it can go to higher angles. Excuse me. For example, here to have 10⁻⁹ bit error rate ratio, it can go to 65-degree angle, considering an 80-degree beam divergence angle. For a clear coastal ocean, it has to be smaller, which means that this angle here needs to be smaller to work. Why? Because as I said, we have lots of lost power, so the receiver needs to be in the direct line of sight of the transmitter. And as said earlier, it doesn't work for coastal or turbid harbor, whatever the angle we use. And obviously, when we approach a square angle, we can't we do not receive any data. So in conclusion, we did the implementation of optical CDMA codes with no wavelengths overlapping in UWOC channel. It has been studied in this paper, considering the different jello filter type. The inherent code properties allowed a reduction of power loss, resulting in the successful results with achieved bit error rates better smaller than 10⁻⁹. Obviously, considering that the users don't have spectral signature that overlap. So thank you for your attention. If you want to discuss furthermore this subject, here is my contacts. Thank you for your attention, and the floor is yours.